multiple parallelly executing threads. Those threads are not exactly threads as in a vague terminology we use, but those are actually different processes, and they may be scattered across multiple physical hosts, which may or may not be geographically distributed. um, Plus, the MPI can also leverage the multiple cores which are available on the same node. So that way, there is a paradigm where there are processes which are running on multiple processes which are running on same host, and they are utilizing shared memory, and as well as there is a subset of applications which are running across the network, and they are executing on physically different hosts. Um, so basically, there are multiple programming models for parallel programming. uh, the one we are talking about here is basically message passing interface based. However, nowadays in modern clusters, all the paradigms have been mixed up. So you will find uh, local shared memory based parallel execution, as well as the network based execution. However, MPI will act as an integrator to everything. Then there are this OpenMP based application programming interfaces are also there, but those are intrusive intrusive in the sense that you will have to recompile your application with couple of compiler directives, and then you will have to execute your program. So, let's try to focus on how a typical MPI program physically it looks like in the network topology. So, for example, if you are running a parallel program which with four processes on two different or four different nodes. So, in the figure here, let's say P0 is running on node 1, P1 is running on node 2, P2 is running on node 3, and P3 is running on node 4. So in that case, what it does is the P0 being the let's assume that P0 is the main process which has started the entire job on a distributed physical cluster nodes. So this P0 is responsible for distributing the data across multiple cluster nodes and telling them to perform the operation. That operation could be multiplication, sum, division, or subtraction. And then it will, after distributing the data across the cluster, it will, or across the nodes, it will wait for the results. It would it is the choice of the programmer that it may uh, program P0 in such a way that it can also utilize the local CPU. So usually we do that. So P0 will uh, P0 will wait for the results and also perform some execution on that, the processing on the data. And then once all the processes have completed processing the different subset of data, then the results will be communicated back to P0 using these links. These are communication links. Now, these communication links could be of multiple types. In a typical cluster, these links uh, are shared memory links if the processes are lying on the same node, and otherwise these are network links which are high performance, low latency networks like InfiniBand and RDMA capable other networks, Rocky protocol, all those things are there. It could be a normal TCP/IP link also. So that way, that's how the network and the computation are interrelated. Okay. So let's go further and try to understand with the more deeper example. Um, let's try to understand that a sequential program is doing merge sort on this set of array. So you have this data, you want to do a merge sort. So what typically merge sort does, it's a divide and conquer technique. So it will divide the entire data set into two parts, and then um, uh, the process, the sequential process will work on the first part. It will further divide it, and then unless it reaches to the smallest divisible unit, it will keep on dividing the data and then keep on sorting, and then once the sorting is done, it will merge back. How so this is how the sequential program works. But how will the parallel program will do it is, there is a P0, which is root process, which is here, P0. Then there is P1, which is on some other node. Okay, so P1 is here. Okay, so now P0 and P1 will, so P0 will decide, I want to divide the data. It will divide and give second half of the data to P1, and also decide to work on P0. Now on P0, whatever data set P0 has, it will apply merge sort on this subset of the data. Parallel to this, P1 will apply merge sort in this green subset of the data. Once both the subsets are sorted, or the process is complete of whatever task was there, in this case it is merge sort. So then using a network communication, this sorted result will be communicated back to P0, and then P0 will do the final leg of merging again and again, sorting, and then this is how the parallel program finishes in a, so you can see that instead of doing entire array one after another, the divide and conquer technique has divided the data into two sub problems, and these sub problems are in parallel solved by two different processes, and then results are communicated back. So this is where the message passing interface, or MPI, stands. Message passing interface provides you a means to communicate, to allow processes communicate with each other while executing the computation uh, in parallel. And this communication is low latency, as low possible is good, and high bandwidth. As high bandwidth you get is the better. As you get the higher bandwidth, it is better for your program execution. Okay, so this is about this. Now um now uh, I have given you some understanding of how the communication plays the role. So now there are multiple vendors for, providing the communication and allowing processes to communicate. So what happened in the past is that there was a lot of mess happening. So they there were a group of companies who made a consortium and came together and say that, hey, this is not how this is going to work, because you are going to apply your knowledge on your specific hardware and your specific computation resources. I have my own. If, let's say, there is a chance that there is a mix and merge of your hardware and my hardware, or your software or my software, then there's going to be a mess. So what they did is they came up with the MPI forum, which is message passing interface forum, and they came up with a standard that whoever is going to implement a MPI, they has to follow a minimum this set of this is the set which they have to follow. So this is what is MPI now. Since it was formed, there are 3 or 4 revisions has happened. Latest is MPI 4. So this MPI forum governs how the MPI should be implemented, and what all APIs should be there. Okay. So now there are multiple implementations available in open source, in closed source. Uh, that's how it is. So MVAPICH2 is one of the most leading MPI. Dr. DK Panda must have covered this yesterday, and there are other MPI flavors also, which is MPICH3, which is from Dr. Pawan Balaji from ANL. Then OpenMPI is open source MPI implementation. Then Intel has also its own MPI, which is called Intel MPI. So each of all of these MPIs have some unique features, um, some common features, but in the end, they are implementing everything you following the MPI standard. So now let's, any questions till now here? So I don't think I have anything in my QA box. Okay, so let's proceed further. Fine. So let's take a quick look how a typical MPI program looks like. Um, so there are C language interfaces and Fortran interfaces also available. MPI packages usually provide their own compilers, which are just a wrapper script for optimized compilation of the MPI program. These are called MPI-CC, MPI-F90, and MPI-C++. This is for C++ compilation. F90 is for Fortran code compilation, and MPI-CXX is for either C or MPI or C++. Now, if you look at the typical code of MPI program, you have to include this MPI.h. Then standard lib is just, I have, for some prints I have added that, not mandatory. And your main function will look like this. You have to call a mandatory call which is called MPI init, and then you probably want to know your own rank. So this is again MPI. The MPI com rank is the MPI API defined by the standard. It gives you the rank of your own process. Now, if your rank is 0, then you are root process. You are the administrator of this particular set of this task, basically. So if you take an example of integer sort, then this is P0. You do something here, and then if you are a worker process, you're not a root process, then you do something else depending on how you program it. Then once you're done, you have to say MPI finalize. This will tear down the environment and free up all the resources. Once the resources is freed up, your program returns with success. Now, to compile your MPI program, you have to say MPI-CC first.c, and then just like GCC, you have to say MPI-CC instead. And to run your MPI program on, let's say, 2 nodes, let's say this first which you had created, you want to run this on an MPI cluster, then you have to say that MPI run NP2 is how many processes you want to run, or into how many processes you want to divide your task, and then on which all hosts. This gives the dash host file. HF gives you allows you to describe on how many nodes you want to run it, and then your executable uh, you have to specify. Okay, so most of the times there are multiple types of communication calls available in the MPI standard or typical MPI distribution. Mm, the first category is point-to-point communication. If you see in this example here, do something. So if rank 0 wants to send some message to other ranks, but not to all the other ranks, but only to one particular rank, then it will say it will use point-to-point communication. So in that case, you will say MPI send here. Rank 0 is sending the data, and um, uh, other rank, that particular rank will say MPI receive here. MPI receive and MPI send are the APIs. Then another category is collective communications. So in this category, what happens is um, there is usually one sender and multiple receivers, just like multicast. Okay, So you are sending a data. So rank 0 is calling MPI. Hold on a minute. I have some disturbance. Yeah. You can see my screen. Anybody? Hello. Is my screen visible, Ganeshan?
Audible, Devesh.
Yeah. Okay. Good. Thank you for the feedback. Yep. Okay. Yeah. So yeah, in collective communication, what happens is, let's say rank 0 would say that I want to tell. Let's say you are running with n dash np4, and there are four processes, like in the previous example here. These all four are running. Okay, p0, p1, p2, p3, p2, p3. So p0 wants to communicate some message to all of the processes p1, p2, and p3. So in that case, it will, instead of doing one by one after another point to point communication, like p0 sending to p1 and p0 sending on p2 and p3 in a loop, is not efficient. Okay, that's why they came up with collective communication calls. In this case, what will happen is, in this case, what will happen is, um, whoever is calling the call, the collective communication, then the message will be delivered to all of the processes, other than the same self process. In some cases, you can also send to self process. Okay. um, so non-blocking, so yeah, so this is about collective communications. The typical collective call is made like this: MPI all to all, and then once the all to all is called, this is a blocking call. um, unless the communication has been sent to all the other processes, the execution thread will remain blocked here. And similarly, other processes will also have to call all to all. In the This will automatically, internally, MPI will decide, will choose that it is in a reception mode, so it will wait for the messages from the sender process. And using the arguments, you can tell that whether you are a receiver process or you are a sender process. um, but okay, so now what we want to do is, we want to achieve maximum availability of CPU, so that the computation can be done very easily, or in the efficient way. So if, let's say, there is this blocking call, so blocking call will keep on spinning on the CPU. It won't release the CPU. So my CPU is wasted. Okay, this is spinning here, just blocked, and it is the computation is not happening. So what they did is, they came back with non-blocking collective communications. In non-blocking collective communications, a similar I mean, the the message still goes to all the processes which are there in the communication world, but the CPU is freed up immediately. So in that case, what will happen is, if you are calling a non-blocking collective communication call, then MPI I all to all is the non-blocking version. Then what you have to do is, you have to call all to all, and then this execution thread will not block here. It will go and wait. It will let CPU to sleep. Okay, it will ask CPU to sleep and wait until the operation is completed. So so this is how the non-blocking communication is achieved. So this basically yields the CPU for more computation, and achieve more computation and communication overlap. um, okay, so let's move to MVAPICH. And in basically, Dr. Panda must have covered the other day that how MVAPICH is celebrating long term availability, and it's now uh, I think the foremost MPI to be considered whenever people are establishing any MPI cluster. So MVAPICH 2 is is open source, um, and it is based on MPI 3 standard. It is basically derived from MPICH, which I had told previously, but it has some add-on features, some mainly towards InfiniBand, Rocky, IWAP, Omnipath, and TCP/IP based communications. It also provides support for GPUs. It has support for Intel, AMD, IBM's Power 9, and it supports Mellanox, Intel, Broadcom, and Chelsea and EFA adapters. So if anyone is interested, they can see this documentation here, link given here. Okay, so I would like to take a pause here, and if there are any questions, I would like to address. Otherwise, we will move um, to a hands-on where I would show how to build and compile your MPI applications and the MPI tarball, and run a simple application on Sahasra cluster. Any questions? Okay, I will take it as a no. Just give me a moment while you're thinking. I will try to join the VPN and show you the execution. Ganesh, is my screen visible? This let me know if the font size needs to be increased.
Increase the font size because it's very small in the auditorium actually.
Okay. Better now? Better now? Visible?
Yes, it's visible, Devesh.
Okay. Good. So so let's see how to build and install. So I have already taken this tarball from the website. You can easily say wget and from the link, and you will get the MVAPICH2 tarball. So what you have to do is untar it. This will give you this okay, and then okay. So these are some steps you have to follow. So after untarring, you have to run this configure command, and these are some of the basic options which you would find in your um, the documentation of MVAPICH2, and so basically CH3 MRail, the explanations, proper explanations I have been given there. And then with RDMA, meaning it will, the MPI will be built with RDMA capability. Uh, uh, then you have to specify the prefix. In prefix, I'm saying that you install it in this particular path, MV2236. And there are a couple of options, like because we have a job scheduler here installed here, you have to say, you have to tell it in which path the job scheduler is present. So if you, when you will run this command, you will see the output like this. So right now what we are doing basically is we are building the MPI implementation. This is not the MPI application. This is MPI implementation. Okay. And we are building MVAPICH2. That's the flavor of MPI standard. Yeah. If you don't see any errors, you will see this message which says that configuration is completed, which means you can now build the MPI. Because I had already built it previously, I will clean this thing. Now the compiler is compiling each and every file which is present in this distribution, and it is coming up with the library. Yeah, this is step takes time. I think in the meantime we can cover this document, where I also wanted to show how is the the cluster in Sastra University, which is your university. So so basically, we have one management node which has 1 terabyte NFS storage. This management node is to provide connectivity and ease of access to the compute nodes. Usually what we do is, in management node we have all type of compilers, and we keep all our source codes and binaries. So this compilation which is happening here is actually sitting on this management node. um, Now this dotted line is the high speed, high bandwidth interconnect, which I was talking about, is RDMA capable. It has latencies of the order of 1 microsecond or less than 1 microseconds for 2 bytes of data. And bandwidth, if let's say if the card is 100G, then line rate will be achieved for 1K of data size, which is very difficult to achieve. Okay. um, Now, so dotted line is the high speed interconnect. Then the solid line with arrows is the regular TCP/IP interconnect. The TCP/IP interconnect is basically used to provide the connectivity to the remote rest of the world, which is using Ethernet. um, and this there is this Ethernet switch which is also connected to the compute nodes. These are compute nodes. Compute 1 and compute 2 are the compute nodes which basically uh, runs your job. I- it runs your job. The MPI job, the computation task is performed by these two nodes. So in your campus you have two compute nodes, one management node, and a Ethernet switch, and a 100G low latency InfiniBand interconnect, which has RDMA capability, and it has a capability to avail login remotely. I'll, so this is okay. So mm, machine learning and AI related loads, you have NVIDIA Tesla V100 16 GB GPU as well. Um, Somebody must have covered the section related to GPU, I guess. So yeah, then one of the important part is it has 8 terabyte of GPFS, which is the parallel file system. Parallel file systems are much faster, way much faster than the regular file systems which we have in your any of your laptop or anywhere, right? So yeah. uh, so these are some screenshots where we are showing that we have Mellanox card. This is an InfiniBand card, and it has a link speed of 10 Gbps. This is about the NVIDIA GPU. I think when this screenshot was taken, it was not running anything. It was free. So um, yeah, so as I told you, you have two compute nodes and one management node. So IBM Power, if you see here, this is the IP address of the IBM Power machine, and T1 and T2 are the compute nodes. I think rest is related to the management. Mostly admin should be able to access it. Um, as a user, you students, you should only have a user account. Uh, Usually these are not, um, yeah, the management activities are not shared with you people, right? Okay, I think so it has a job scheduler as well, which is called PBS. So what the job of the scheduler is that there can be 100 students at the same time, maybe trying to submit or trying to run their job. Now, how to manage the resource, how to manage the compute resource in the efficient way. So what this job scheduler does is It lets every student to submit its job, and it is the responsibility of this job scheduler to run and get back with the run your job and run each student's job and come back with the results. So for a user, for you as a user, it is just fire and forget. You fire the job, give it to the scheduler will arrange the how to run or when to run your job and get back with the results. So this cluster is equipped with the PBS job scheduler. There are some simple commands which probably needs to be shared with the students, where they can, using which they can submit the job and wait for the results. If by mistake they have submitted some wrong job, then they can also delete the job and uh, yeah and use the cluster in efficient way, efficient manner. Yeah. So now I think this compilation is done. Usually, okay, wait. Yeah, we were here, right? I pressed enter here. Yeah. So now this compilation has been done. So basically, MVAPICH2 also has one of the very small micro benchmark application, which is called OSU benchmark. Whenever I am building the MVAPICH2 tarball, those are also built along with. mm, so yeah. Okay. So if you check the path where I had installed, um, this is where this is what I had installed, right? MV2236, and this was the path. So now here the entire MPI has been installed, and these are, as I told you, right? MPI CC is provided by MPI. So here is the compiler, MPI CXX, and here is your MPI run command. Then F90 is the Fortran compiler, and MPI C++ is the MPI C++ compiler. Um, so in the interest of time, I will skip compiling any application, because I want to leave at least 10 minutes for Q&A. So let's try to see. So the benchmark which I was, or the micro benchmarks which I was talking about, are built and installed in this path. Point. Okay. So these are some of the standard benchmarks. Let's say OSU BW is to measure the bandwidth of the network. OSU latency is the latency measuring benchmark, and these are all point-to-point communication. If you look at the source code of these, you will find that these all are using MPI point-to-point communication APIs. So let's try to have a quick run. Yeah. So as I told in my presentation, we have to run our job using MPI run command. MPI run underscore RSH is just a variant which will use SSH to launch your command. So you can read more about these commands in the documentation. Then np2 is I'm asking MPI to run two processes, and host file is these two. Host file contains the name of host where I want to run, and which benchmark or which executable I want to run is listed here. Like I want to run the OSU latency benchmark, which is point-to-point benchmark, and if I press enter, then it will show me that for 0 bytes it took 1.45 microseconds to reach the data of 0 bytes from node 1 to node 2. So 1.45 microsecond, achieving this latency is really difficult. Okay, I mean, it is not. If you run the same benchmark on TCP IP, so right now it is running on InfiniBand. If you run the same benchmark on TCP IP, the minimum thing you will get is somewhere around 5 microseconds, or maybe more than that. And likewise, keeping this latency number low as possible for maximum amount of data range is also very difficult to achieve. So if you see here, till 128 bytes of data, it is only in the range of 1 microseconds or 1.2 microseconds on average. 1.5 rather, yeah, 1.5 microseconds on average. Only after that it increases. Okay, so yeah, so this is about latency. And what is latency is you're sending 0 bytes from node 1 to node 2, and then you're hearing back the echo. The same data is replied back to the initiator node, and then whatever time it took, you divide it by 2. This is called one-way latency. Okay, and this tool reports that one. So if you run the bandwidth, you would find that so almost for 2K message size, we are almost reaching the line rate, which is, this is nearing about 10G. This is megabyte, so multiply it by 8. Yeah, I think still there is some more optimization and tuning could be needed to, get the maximum performance. Okay, quickly, one of the collective communications I would like to show is, for example, all to all, which we were discussing, and so this is what the latency we achieved when all to all was run. So basically, it just had to wait. The root process had to wait only for 2 microseconds, 2.68 microseconds before all to all communication finished between two processes. If you run it for more processes, let's say per node there will be 4 processes, I will make it 8. So total 8 processes will be run, 4 on node 0, 4 on node 2, and you would see the difference. See, now for 1 byte message size, the root process had to wait for 4.49 microseconds. Okay, sorry. Yeah, earlier this was 2.68 microseconds when it was 2 processes, and now it is 4.49 microseconds. So this is how they scale up. As you grow the number of processes, the time needed to finish your job increases. That's why it is very critical to keep the latencies minimum. And MVAPICH2 is being from the house of Dr. DK Panda and his associates, is really a good MPI. It does not put too much of overheads in providing all these basic APIs. Okay, one last thing I would like to show is, indeed, when I'm saying run 16 processes, then indeed there are 8 and 8 processes running on both the nodes. So this can be seen very easily just by running a top command here. Oh, sorry, not here. Then I will say SSH T1IB. So this is my compute node T1IB, and I would say top S1. So right now there is no MPI related job you can see. Now I will start the job here, and you can see 8 all to alls are there. 1 2 3 4 5 6 7 8. 8 all to alls are there which are running, and the moment the job will finish, all these will disappear. Yeah, they are gone. The benchmark is done here. Okay, so basically why 8 here? Because we were running on 2 nodes. So if I log into the second compute node and do the same thing, do the same top command, you will see rest of the 8 processes on the second node. Okay, yep. So I think this is it. Any questions? Suppose in a cluster of 16 CPU, if I create 20 processes using MPI, then how the processes will be allotted in the cluster? Right. So this is depending on the topology. What there are multiple topologies you can select. You can using MVAPICH2. So you have 16 CPUs, meaning 8 and 8, and you are creating 20 processes. So in this case, actually, this is not efficient to run, or we would say that you are oversubscribing your cluster. You have total 16 cores or 16 CPUs. 20 processes would basically, um, yeah, more than 16 you meant, right? Yeah, so 20 processes will oversubscribe the cluster, and it is not efficient to do it that way. So usually this is a very I mean you have to be careful about how many processes maximum you can run on a given cluster. So more than 20, more than 16 would definitely bring down the overall performance. It's not recommended. However, the distribution, as long as the distribution of processes are concerned, MPI will not stop. I mean, it will, depending on the policy which you have chosen. Usually, it is round robin. So so your 10 processes will be started on node 0, and remaining 10 will start on node 2. But all of them will compete for the CPU. Because there's no free CPU for a particular MPI process. So there will be a lot of juggling of CPU between processes. So that's how the performance will come down. So if you do not have any further questions, I'll stop here, and thank you all.
Yes, thank you for the presentation. I hope there are no questions from our side too. So it was a wonderful presentation actually. So thank you so
Okay,
much.
thank you. Yep. Okay. Bye bye.